exponential logarithmic equations. There's a couple different types of exponential equations that we can deal with. Kind of show you the easiest, I guess, first. It's kind of like a one-to-one relationship that we talked about here that allows us to solve these. Meaning that, and you guys know this from seeing things with fractions. Like if I said 2/3 is equal to like x over 3, what does x have to be for those things, or the side on the left and the side on the right, to be identical?
Terrible.
X has to be 2. Okay. That's kind of a one. That's what we're referring to here as a one-to-one relation. Okay. That's 1-to-1. That's got to be 1-to-1. Does that make sense? Okay. So same thing here. If I have like 2 to the x equals 2 to the 4th, what's x got to be for the left-hand side to be identical to the right-hand side? 4. X got to be 4. Okay. Is that pretty easy?
Yes.
Okay. So it obviously gets harder. So let's do a couple examples here. They're a little bit more difficult. All right. So a lot of times when you're seeing these questions with exponentials, they don't initially start you off with the same base. Okay? But we should have somewhat of a foundation of laws of exponents that allow us to manipulate bases. Okay? Now this doesn't always work. Okay? But what is nice is to have maybe a rough idea of your small kind of bases to a power. So for instance, like I know 5 to the first is 5. 5 squared is 25. 5 to the third is 125. 5 to the fourth is 625. Okay? If I can keep like a small understanding of those, maybe go 2 squared, 2 to the third, 2 to the fourth, 2 to the fifth. Maybe I know 3 squared, 3 to the third, 3 to the fourth. Maybe I know 4 squared, 4 to the third, 4 to the fourth. Does that kind of make sense? Usually you don't, at least in practice problems, you don't need anything much bigger than those numbers. Because if I go, 5 to the 7th, that's a very, very large number. Okay? And usually we're not dealing with things that are that big. But we should be able to hopefully recognize some relationships between that number and that number. And the hope is then that you can take that number and rewrite it so that it has a base of 5. And that should be 5 to the 4th. Okay? 5 times 5 times 5 times 5 is 625. Is it okay? If you can't do that, I'll show you a technique here in a little bit that gets me the same exact answer, just using a different approach. Okay? But now, over here on the left, I get 5 raised to 3x minus 2. What's nice about that? Bases are the same now, right? So that one-to-one relationship says if the bases are the same, shouldn't those two things be the same? So that develops in the two-step equation here, where we're going to add 2 divided by 3, and we solve for x there. When we solve for x there, we can plug it back in up here. Okay, and this is, you can always check it, just like anything else in algebra. You can always check yourself. Plug back in the original problem. Take 2, plug it in, I get 3 times 2 is 6. 6 minus 2 is 4. Equals 5 to the 4th, the same thing, 625. Yeah. Okay. It's actually the relationship that we set up so we can start this problem. That's only doable if I can, take, if that was 626 over here, I couldn't do that approach. I had to do something else. Okay. But in this case, we can rewrite both bases so that they're the same. Therefore, the exponents are going to be the same. Is that something we can do? If you take the ACT, and you juniors are going to be doing that hopefully multiple times maybe this year. The ACT a lot of times has one of these questions on it towards the end. And they're usually ones that you can either do this with, or they're already in that format. They're already 5 raised to 3x minus 2 equals 5 raised to the 4th. Okay. Something else I want you to realize is that these are just equations, right? So I should be able to take 5 raised to the 3x minus 2 and get that exponential there, right? And I should also be able to take y equals 625. Y equals 625. Get that line there. Okay, now I'm going to have to adjust my window here. Let's go y-axis. Okay, do those two things intersect at x being 2. Does that make sense, everyone? You can do that on your TIA 384 as well. Just the only thing on that is changing that window might be a little bit of a longer process than what it is on GeoGebra. Okay? But when you solve these equations, it is where the two sides, the two graphs from both sides intersect. What happens a lot of times, though, is that that number usually isn't an integer when we deal with exponential equations, like 2. Okay? It's usually something pretty ugly, where we want the exact answer, not the rounded answer, and we'll go through the process of doing that here in a little bit. All right, so that middle one. I look at 8 and I look at 32. If I take 32 and try to rewrite it so it's got a base of 8, well, 8 to the first is 8. 8 squared is 64. I skipped over 32, right? So I can't rewrite 32 as a base of 8. So then if that can't be done, I look at both numbers, 8 and 32, and I ask myself, can I rewrite both to a different base? And you see, look at 8, and maybe you think 4, right? I take 4 raised to the first power, you get 4. 4 raised to the second power gives me 16, right? So I skipped over 8. Okay? If I go 4 to the third, I skip over 32. So 4 is not the, even though they got a common factor of 4 in them, that's not the base I'm going to write it at. But if I look at another common factor they have in them, it's 2, right? Okay? What can I write 8 as with a base 2? It'd be 2 to the what? 2 to the third. So 2 to the third, that's 8. Okay? We should have 8 raised to 2x, shouldn't we? So when I write 8 as 2 to the third, I still need to rewrite it at, or sorry, still raise it to the 2x. So 2 to the third raised to 2x. Now 32, 2 raised to what is 32? 2 to the fifth. Okay. Now, what is this really tough? 2 to the third to the 2x. That's really 2 to the what? I heard it. 6x. You got a power to a power. Don't you multiply those things? So then I got 2 to the fifth. So 6x equals 5, right? X is 5/6. You plug that in. 8 to the 5/3. Once you multiply that by 2, right? So 8 to the 5/3. Type that in your calculator. 8 to the 5/3. Now, when you type in your calculator, you got to put the 5/3 in parentheses. Otherwise, they'll take 8 to the 5th, calculate that, and divide that by 3. We don't want that to happen. We want 8 to the 5/3 gives me back 32. Okay. You could sit here and think, okay, what can I could do? Maybe a trial and error type thing. Okay. Knowing that 8 squared, if x was 1. 8 squared would give me 64, right? Okay. So then I've got to find an x value of 8. If x was 1, I'd get 64 here. So then you start thinking, well, x has got to be less than 1 then, doesn't it? To get 32? So you can maybe start doing a trial and error type thing, and maybe zero in on 5/6. But that's going to be very, very hard, just kind of in general, to do that. Okay. So that's one approach. Rewrite the bases so that they're the same. The last one, I guess. No rewriting having to be done here, but I just wanted to show you that you can develop, when we have these two bases to be the same, you can develop algebra that is nonlinear. Okay? There we got x squared equals 16, right? So solve that, you get plus or minus 4, right? Okay? So when you develop these equations from looking forcing the bases to be the same and looking at the exponents equating, you might get linear equations, you might get quadratic equations, you might get things you have to factor, you might get things that are just in general ugly, okay? There may be even cases where you get another exponential equation, okay? It's just kind of the nature of the problems that we see. I just don't want you to realize or focus in on just having to deal with linear equations, okay? So that's a potential thing to happen. Now, here's my question. That's a great tool. It works. It's kind of the, as I'm going through just algebra in general, if I've got, 2, 3, 4 different ways of doing something, I'm always going to look at the problem and think, okay, what is the most efficient way? Okay? So when I see those problems, those are the most efficient ways for those problems. But there are other ways to solve those problems. Okay? And those other ways, we really talk about them or use them in the event that the bases cannot be rewritten as the same. Okay? We'll come back and we'll redo this one here using the technique that I'm about to teach you and see that we do get to both ways. But here are the general guidelines for dealing with any exponential equation, regardless of whether you can rewrite the bases or not. It says isolate the exponential expression on one side of the equation. Okay? It's not always necessary to do that, but it's going to make your rules of logarithms and exponentials a little bit easier to deal with if you do that. Okay? There will be times where if you don't do that, it works. You'll be fine. There will be times where if you don't do that, you won't be fine. Okay? So it's just good practice to do. Step 2 says take the logarithm of each side. Okay? And we're going to use the law of logarithms to bring down the exponent. Remember, this is going to be kind of your best friend with this stuff. Remember that law of exponents we talked about Friday? Okay, if I have the logarithm of some base of a raised to an exponent, you can rewrite that as c times the logarithm of that base of that argument. Okay? The purpose of using that is that this c here, that's going to be like the 2x plus 2 or the 3x minus 5 or the x squared that was in the last problems. Okay? It's going to be the exponent. It's going to have variables in it, and that will allow that exponent to come out of the variable. Okay? Or sorry, the variable to come out of the exponent. All right, and then once we do that, once we apply that, we just solve for the variable. So we just use our algebra 1, algebra 2 skills to isolate the remaining variable. These aren't too bad. They're not extremely difficult. There are just a couple kind of technical things that I think you want to pay attention to, or you'll get yourself in trouble. We'll talk about that as we do the next exam. So here we got the equation 3 raised to x plus 2 equals 7. In this case, there's no way for us to rewrite 3 so that it looks like 7. Well, there is, but it's not in a really nice way. Okay? The number that we could do this with is the answer that we're going to get here in a little bit. Okay? So, can't rewrite 3, can't rewrite 7 easily, right? So they have the same base. So this is the approach that we want to take. We want to isolate the exponential portion, which that side is already isolated. The 3 raised to x plus 2, that's all by itself, right? The next thing you do, step 2, was to take the logarithm of both sides. Now, here's the thing. When we say take the logarithm, whenever that's an option, and that's the directions they give you, or the rules they tell you have to use, and they just say take the logarithm, it does not matter, because they didn't say what base, right? So the base is totally your choice. You want to use log base 2, use it. You want to use log base pi, use it. However, your technology, it's really hard to use those things, isn't it? Okay? What are the 2 most common logarithms, bases that we want to use? 10 in natural log. 10 in, or sorry, natural log. 10 in e, right? Which the base e then provides the natural log. Okay? So those are the 2 that we want to use. Now, I'm always going to use ln. Okay? Just kind of get you kind of geared towards other courses. You get to a calculus course, you get to Calc 2, whatever, you get to a differential equations course. They're going to use natural log just because it's more natural. It's more useful. A lot of the applications that we use ln inside of, and we use this process inside of, those involve E anyways. You remember that fish problem we talked about a couple days ago in WebAssign? I had like it was like to give you like D over like 1 plus E raised to the negative KT or something like that. But that was a logistics model that incorporated E, right? Well, if I wanted to solve for that exponent T in that problem, the best basis to use would be ln because of the E that showed up in the original model. Does that make sense? So because that happens a lot, I'm going to use ln, and hopefully that gets you kind of geared towards other courses as well and prepared for those. Because it doesn't really matter. And I can show you some calculations here in a little bit that proves to you that it doesn't matter. Okay? But once you isolate this, you're going to take the natural log of both sides. Remember, you can do anything you want to an equation as long as you do it to both sides. So I'm going to do that. Take the natural log of both sides. Well, if I do that, what's nice is that this here on the left-hand side now became this rule. If I have log base b of a to c, doesn't that become c times log base b of a? You remember saying that Friday? Well, now that c term is the x plus 2. So we take that x plus 2, and it comes out in front. And now I have ln of 3 and my ln of 7. Okay? Now I purposely left something out when I wrote this. And it has to do with that x plus 2. Okay? Because this is the most common error that I see with this stuff is we know our properties, we know how to address it, we know how to isolate x when we address our properties and use them correctly. But just because of notation stuff, we mess things up. Because if I take that x plus 2 out front, and I write down ln of 3 equals ln of 7, and then just temporarily I forget maybe what this x plus 2 represented, and I want to try to solve for x. Well, the way I wrote this, doesn't that look like I have x plus 2 times ln of 3? Where really I have the quantity x plus 2 times ln of 3. So I get a lot of people at this stage here to subtract 2 ln of 3 from both sides and think they solved for x. But really what you need to do is realize that when you have a quantity, and this is just algebra in general, when you have a quantity, force yourself to put parentheses around it wherever it goes, wherever you do with it, put parentheses around it, because then you're not going to mess up the next couple steps. Okay? So what does that tell me? If I have x plus 2 and then ln of 3, ln of 3 is just a what? What kind of thing is ln of 3? Isn't this just a number? Okay, is that what you said?
That's what I said.
Oh, I didn't hear you. Speak up! So it's just a number, right? Okay. So I have x plus 2 times just a number. What does that tell me to do? Okay, divide by that number, right? I've actually got two options. I can divide by that number, or can I distribute it? Yeah, either way, it's fine. I'm going to divide it. I think that's the best thing to do. So you divide both sides by ln of 3. Come over here, get ln of 3. So now I have x plus 2 is equal to ln of 7 over ln of 3, right? Now, subtract it. So x then is equal to ln of 7 over ln of 3 minus 2. And there's your solution. Okay? Not a really nice number. Not a number that you would have kind of found using guess and check techniques. Okay? If you would have used your calculator to approximate that answer, that's all your calculator is going to do is give you an approximation, because you're going to have to round that answer. Okay? Because it's not as an exact answer like this is. But if I type this into my calculator, go ln of 7 divided by ln of 3. Just be careful with your parentheses because it will open those up for you. Make sure you close them. Okay, so that's going to do that division first, right? Order of operations calculator says do division first. So that's what we want. We want the ln of 7 divided by ln of 3 first. Hit, calculate that, and then remove 2 from that. So this is the number that we're getting then. That's the value of x. Not a really nice number. If I would use my calculator to find that intersection point, I would have to round that to answer the question at some point. Okay? Where if I have ln of 7 over ln of 3 minus 2, that's the exact answer, right? You guys remember back to geometry, and I force you probably after Christmas for that whole semester to work on exact answers and writing answers as exact values. This is one of the purposes for that, okay? Because we want to know ln of 7 over ln of 3 minus 2, not negative 0.229. Okay, I would rather have ln of 7 over ln of 3 minus 2. But here's how you can check yourself. That is your x value, right? Okay. A couple different ways of doing this. You can hit the STO button right away, and it says answer, which is referring to this number here, and then hit X and hit enter. And when that number shows up again, what it means is that anywhere that I've got X typed in, it's going to use this number now. Does that make sense? So I'm going to take 3 raised to the x plus 2. Okay, so now where my calculator sees x, it's going to evaluate it with this number here. So hit enter, and it gives me that 7 back, which is what we had in the equation, right? Give me the 7 over here. Okay. Just wanted to show you that ultimately it does not matter what logarithm you use. Because if I would have used instead of ln, let's just say I used log base 7, or not log base 7, log base 10 of 7 in log base 10 of 3. Do I still get the same negative 0.228 number? Yeah. Okay. Those are the two kind of easiest logs to use because basically, especially their technology, they have their own buttons. The other bases are kind of hidden throughout the functions they calculate, and they're kind of a pain in the butt to type in. But any base is perfectly fine. Is that okay? Okay. A lot of times, the base of the logarithm that you want to choose, because you know it's up to you, if you can choose a base that is consistent with the base that's inside your exponential, for instance, maybe, and I'm not going to get into this with you and show you how to do this because it's just going to consume a lot of time. Maybe that first one, because the base of the exponential is 5, maybe the best thing to do is use log base 5. Because in that middle one, we ended up with the base of the exponential be 2. The best thing might be to use log base 2. Because what happens is that you're able to use some of those properties. Remember those 4 properties we talked about on Friday at the beginning of class? And we also talked about probably on Wednesday in class as well. You're able to use those properties maybe a little bit more efficiently and quicker to solve the equations. Maybe later on we'll have a little bit more time to discuss that, but that's an option. But nonetheless, if you don't do that, it doesn't matter which base you choose. So let's do this first one here. We did this one already. We did the 5, the 3x minus 2 equals 625. We got x to be 2. We've already done it one way. Let's make sure that we can verify that answer using the approach we just talked about. The approach we just talked about said take the logarithm of both sides, right? Okay. So I'm going to take the log of 5 to the 3x minus 2 and the log of 625. Okay. That allows me to get 3x minus 2 to come out in front. Something like that, correct? Now, you start to see that as you start doing these, a lot of them are very kind of pattern oriented. Because in the last one, we did this, brought that quantity out, then we divided by ln of 5, right? I guess the last one was ln of, I think, 3, but it's the same process. Divide by that. Come over here, divide by that. So now I get 3x minus 2 is equal to ln of 625. Divide by ln of 5. Add 2 to both sides, right? I'm just going to cheat a little bit. rewriting, add 2 to both sides, and now what do I do? Divide by 3. Now there's a quantity on the right-hand side that I have to divide all that stuff by 3, and that's kind of a pain in the butt. What's a better way of dividing by 3? Multiplying by a third. And then if I multiply both sides by a third, I get x on the left, and now this is a quantity over here, right? So I need to multiply, just basically distribute that 1/3. So that 3 will show up there. And then 2 times the third, the 3 shows up there. Absolutely not even close to looking like 2, right? I went to our calculator. And we could do maybe some laws of logarithms and stuff like that to see that that is indeed basically showing that this here is 1/3. And then, or it's not 1/3, would it be 1 1/3, or 4/3. We could do that, 4/3 plus 2/3, and it gives you 2. But your calculator is going to do it so much quicker. So we go ln 625 divided by, now, you just got to make sure you put this denominator in parentheses. We want that multiplication to be done first before the overall division. So type that in, and then plus my 2/3. And we get 2, which we already knew should have been the answer, right? So it just proves to you that you can do, whenever you come across an exponential equation, you can use that process. Hopefully you see that it's a little bit easier, at least in this problem, to change the bases first, right? So that's, hopefully as we go through math, we recognize the necessity for being able to do a question multiple ways, just because of the efficiency. What I do want you guys to understand, because this is another problem I see a lot, I cannot rewrite that. Remember, ln of 625 over ln of 5 does not equal the ln of 625 over 5. Is that okay with everybody? Make sure that you know that those two things are different. Okay? I get people to want to rewrite that all the time because it makes things easier if you're able to do that, but you're not able to do that. Just be careful with that. Let's go to, let's do this one. This is kind of a situation where, if you remember at the beginning of class, I told you, I gave you those 3 guidelines or 3 steps, and I said isolate the exponential. Okay? So here we want to isolate the exponential term, e to the x. That's what we want to isolate. But if we fail to do that, we should still be able to, at least in this one, still get the right answer. It might look different, but it's still the same value. Let's approach this maybe the most appropriate way. Let's try to get the e to the x by itself. Remember, 3 is a multiplier. 3 is essentially a coefficient here. So I want to get that to the other side. So how do I get that to the other side? So e to the x is equal to 10/3. Okay? Now here is a purpose, because e is in the equation, right? So here it becomes a situation where it makes sense to always kind of use ln, because every once in a while, when e does belong, or is in the equation, now if I have ln of e to the x, I'm going to take ln of both sides, or the logarithm of both sides, I get something that looks like that, right? Now if you remember from Friday, we had a particular property, and I'm going to write it over here. This is the reason we talked about those properties. We had ln of e to the x. We said that was x because ln is the same thing as log base e of e to the x. Well, what do we have to take this e to get that e to the x? Just x, right? So knowing those properties allows me to quickly evaluate that and say ln of e to the x is just x. Okay? Or, I probably shouldn't put or there, but put it there. Or maybe your person says, I don't recognize that property right away. And you say, I want to use the exponent property with logarithms. So I bring the x out front, right? So x ln of e is equal to the ln of 10 thirds. Do you remember what ln of e is? It's 1. Okay? So you x times 1 there, right? Or, if you're a person who doesn't realize that, you could still write this answer as x equals ln of 10 thirds divided by ln of e. You type that into your calculator and get a decimal, maybe that's what they want. Are you going to get the exact same decimal that anybody else that typed in just ln of 10 over 3 is going to get? Yeah, because ln of e is just what? It's just 1. The hope is, though, that you don't, on a homework assignment or a test or a quiz, in my class, I don't really care too much right now, because it's maybe the first time I'm dealing with it. But if you're in like a Calc 2 class and you leave ln of e inside your answer, they're probably going to say something to you about that. Okay, because it's a common fact that we should know that goes to 1. Okay, but all those things are appropriate. Okay, that's our answer, ln of 10 over 3 for this question. And you type that in your calculator, store it as x, and then write 3e to that x should spit back 10. Okay, so if you think about what we're doing there, we're taking 2.718. We're taking, and this is I think this is kind of weird. We're taking an irrational number, okay, which never ends and never repeats, right? And we're raising it to some number that most likely is also irrational, okay, and then tripling it. And what does that produce us? A rational number, okay, which I think is interesting. Maybe you don't. I'm kind of a nerd, I guess. But can we do it this way? Can we take the ln right away? Think about this. Doesn't always work, but in this case, I think it will. So look at that. This is the kind of the reason why those guidelines at the beginning say to isolate the exponential part, because if you don't, it's going to incorporate some logarithm properties or laws that you don't maybe want to use. Because when I look at that, doesn't that mean ln of 3 plus ln of e to the x? Did everyone do that on Friday? I have a product of two things inside my argument. I can separate them as addition. And I got ln of 10 over there. Well, what's ln of e to the x? X. So we got ln of 3 plus x is equal to ln of 10, right? Okay, so how do I solve for x? Okay. So if you are a person that wrote that answer, that does not look like ln of 10 over 3, right? As what maybe your neighbor got. If you type that in your calculator, you get the same exact decimal. But why? When I have the subtraction for two logarithms that have the same base, it turns into division of their arguments, right? Okay? So you do, in fact, have the exact same answer your neighbor does. You just maybe wrote it in a different format. Does that make sense? Okay? So that's a situation where not isolating your variable term or your exponential term all by itself, getting rid of the multipliers, you're okay. Okay? Now, if we had something like this one, just because there's so many more operations that are occurring here, I think if we do this with this one, or do the same approach with this one, we run into a roadblock and kind of get stuck and can't progress any further. Okay? So this one, it makes sense to kind of do all that algebra prior to taking logarithms. Okay? So we see that, hopefully maybe can we isolate that thing, and then hopefully maybe just isolate that. All right? So kind of going through the algebra to do that. When we have fractions in equations, this is a rational equation. What do we like to multiply everything by? Common denominator. Common denominator here is just 1 plus e to the negative x, right? So if I do that, I just get 50 on the left-hand side, and I get 4 times 1 plus e to the negative x, right? Okay? So we multiply to get rid of fractions, but what we're going to do now is we're going to divide, because it's going to bring back fractions, but it's going to make this seem a little bit simpler. Okay? We're going to try to isolate this. So divide both sides by 4, and you get 25 halves is equal to 1 plus e to the negative x, right? Okay, so some people say, well, you multiplied to get rid of fractions. Well, I didn't necessarily multiply to get rid of fractions. I multiplied so I can get the variable out of the denominator. Okay? Now, think about isolating the exponential part. What would I do? Subtract 1 from both sides. So does that give me, what, 23 halves here? 23 halves is equal to e to the negative x, right? Now what can I do? Yeah, once you have the exponential isolated, take the logarithm on both sides. I'm going to take the ln of 23 halves is equal to ln of e to the negative x. Okay. Now just going off one of the properties we talked about on Friday, whenever you have ln of e raised to an exponent, that is always going to simplify to that exponent. Okay. The rule right up here. So if I had yeah, you're right as well. Log base e of e to the x. E raised to what will give me that thing right there? X. So if I had something like log base e of e to the 3x, what would that be? E to the what will give me this? 3x. So now it's that thing, but it's negative x, right? So doesn't this thing just go to negative x? That make sense, everyone? Okay. So now I have ln of 23 halves is equal to the opposite of x. So the opposite of ln of 23 halves is equal to x. And we should be able to check that every single time you guys get an answer. Go back, grab your calculator real quick. Not only is it going to verify that you've done the work right, but it's also going to get you practice at maybe understanding your operations on your calculator a little bit better. I'm going to let's do it this way. So let's go negative ln. I'm just going to evaluate this. 23 over 2. Hit enter. Okay, so that's the number I get, right? Now I'm just going to type in this left-hand side. So I get 50 divided by. Now because this is a quantity on the bottom, and there's operations that I want to be done here first before I divide it through the 50, right? Okay. So I'm going to put parenthesis 1 plus. Now second, there's two places, guys, and I didn't realize this until the beginning class because I never use it. But there's an e over here as well on your division sign. But there's an e raised to the x over here on your ln. I always use that one. Because it automatically opens a parenthesis for me up there, and I'm always going to need that. But now it's negative x. Okay, so hit my minus or my negative key, and then hit the x. Oh, I guess I can't because I didn't store x yet. So actually, I got to type in negative ln of 23 halves. I'll show you a better way here in a moment to do this. Then hit enter. And it does give me that 4. Okay. I wanted to type in x here, but I realized that when I look at this, I didn't have that thing stored as x. So this may be an approach people want to use. Once you hit enter there, hit STO, and then hit X. Okay. And now I can come back to the left-hand side of my expression. Instead of typing in the expression that I had for x, I can just type in x. And then close off the parenthesis for the denominator. And it gives me 4 that way. Okay, so those are some techniques. There's also, when we talk about exponentials, they're tied directly with logarithms, right? So that's a series of exponential equations. Okay. The next thing we'll talk about is logarithmic equations. Okay. So that's hopefully what we introduce tomorrow. My plan is, and I told you this before, 4-1, 4-2, and 4-3. I'm going to keep those due Wednesday night. Okay? 4.4 and 4.5, I'll leave those things open throughout Christmas break. But my hope is that, you know, those have been open for a little over a week now, that you've been working on them, not procrastinating until 3.